Organic chemistry, quick revision. Organic chemistry is the section of chemistry that deals with organic molecules, and all organic molecules contain carbon atoms. They are mostly formed from living organisms, but we can also be made synthetically. To represent organic molecule, you can use empirical formula, which is the simplest whole number ratio of each element in a compound, or use the molecular formula, which will give you the exact number of each element within the compound. You can also use the general formula, which is a type of empirical formula that represents the composition of any member of an entire class of compounds. Structure formula will show the arrangement of the atoms in the molecule, and then the displayed formula, which will give you the symbol of all of the different elements and their bonding. Homologous series. So a homologous series is a number of compounds which have the same general formula and they have the same functional group. And we can use the general formula to work out the molecular formula of any member of the homologous series. They differ by CH2 from in their molecular formula from the neighboring compounds, and they show gradual variation in their physical properties such as melting point and boiling point. However, because they have the same functional group, so they share the same chemical properties or same reaction. The main homologous series we're going to learn about are hydrocarbons, and they include saturated hydrocarbons represented by alkanes, and they are called saturated because they don't have any double bond between the carbon atoms. They only have single covalent bonding. And then there is the unsaturated hydrocarbons, which are represented here by alkenes, which have this double bond, so they are called unsaturated. We will also learn about alcohols, and alcohols have the functional group of OH. Carboxylic acids, which have the functional group of carboxyl group, which is C double bond OH, and then esters, which have this functional group, which is COO. To name the different organic molecules, we will use a prefix and a suffix. So the prefix will always refer to the number of carbon atoms in the chain or in the molecule. So if there is one, it's called meth. If there are two carbon atoms, we're going to use the prefix eth. If there are three, it's prop. Four, it's bute. Five, it's pent. And six, it's hex. So this is going to be always the prefix of any compound. And then the main homologous series you need to know, and the different suffix we are going to use. For alkanes, we're going to use the suffix ane. An example of that is propane, which is an alkane with three carbon atoms, as we use the prefix prop and then the suffix ane. Alkenes are the second one, and we're going to use the same prefix, which refers to the number of carbon atoms, and then the suffix ene. An example is propene, which has three carbon atoms and a double bond, so it's propene, an alkene. Alcohol, we use all OL at the end, so we remove the E from the alkane name and replace it with OL. So we have something like ethanol. Ethanol is an alcohol with two carbon atoms, 1 and 2, and then it has an OH, so it's called ethanol. Carboxylic acid, we remove the E from the alkane name and replace it with oic acid. So if we have two carbon atoms, then it's going to be called ethanoic acid. Ethane coming from ethane, and then oic acid. And then the esters, and esters we use a different naming, different part. The first part refers to the first part here, which comes from the alcohol, and then we call this an alkyl. We name it as the number of carbon atoms. So if it's coming from methane, it's going to be, or from methanol as an alcohol, we're going to call it methyl. If it's two carbon atoms, it's going to be ethyl, and so on. And then the second part that comes from the acid, we're going to replace the oic acid with OH. So we have something like this. And as esters come from a reaction between an alcohol and carboxylic acid. So we have to name both. So the alcohol, as we said, we're going to be alkyl. And the part that comes from the carboxylic acid is called OH. So this one, the acid here has two carbon atoms. So it's ethanoate, and the alcohol only one carbon atom, so it's methyl ethanoate. We need to learn about isomers when we talk about organic molecules, because in organic molecules you could have two or more different molecules that have share the same molecular formula, but they are different compounds. So we tend to call these isomers. And there are three types of isomers: chain isomers, position isomers, and functional group isomers. So what's the difference between all of these? Chain isomers, they are compounds which have the same molecular formula. However, the carbon chain connection is different. For example, if you have a compound that has a molecular formula of C4H10, you could have one of these two compounds. The first one is a simple butane, 1, 2, 3, 4 carbon atom, or you could have this compound which is methyl propane, where you can see that there is a difference in the chain here. There is a methyl group here coming from carbon number 2. So the four carbon atoms are not connected in a chain, but there is some change here. There is a branch here. So these two are two different compounds. They both are alkane. These two are chain isomers. They have the same chemical properties because they have the same functional group. However, they have different physical properties because they are different compounds. The second type of isomer is the position isomer. In position isomers, the functional group is at different position on the carbon chain. For example, C4H8, we're going to have one of these two compounds. We're going to have but1-ene or but2-ene. The difference between these two have the same functional group, which is the double bond between the carbons. However, the position of the double bond for the first one comes in starts with carbon number 1, while for the second one with carbon number 2. So if you start this carbon 1 and this is 2, so this is but1-ene and this is but2-ene. 2 here refers to where is the double bond, where we can find the double bond. So these are two different compounds. However, they still have the same functional group, so they have same chemical properties. However, they have different physical properties because again they are different compounds. The third type of isomers is the functional group isomer, where here in this case the different compounds we're going to have the same molecular formula but different functional group. For example, C4H8O2, we could have the first one, which is butanoic acid. The functional group here is carboxylic acid, or we can have methyl propanoate, which has the ester functional group. So these two will have different chemical properties now because they have different functional group. However, they also still have different physical properties because they are completely different compounds. So all of the type of the isomers, they're going to have different physical properties, but only the functional group isomers where there is difference in the functional group will have different chemical properties. So let's start talking about the hydrocarbons. So hydrocarbons will contain only carbon and hydrogen. They can come in a varying lengths and also some of them are branched. They many of them can be found in organic living organisms like in plants, animals, and their fossils. Other hydrocarbons can be prepared in the laboratory. We use hydrocarbons in everyday life, such as we use it as fuel, such as the natural gas, acetylene, propane, butane, and so on, and also some in the petrochemical industry, and the plastics that use are also polymers that come from hydrocarbons. The first series of the hydrocarbon is the alkane, and alkane are saturated hydrocarbon. They only contain single covalent bond between carbon atoms. Each carbon atom can form four different bonds with four different atoms. They can be either carbon or hydrogen. The general formula for alkane is CnH2n plus 2. So this is the general formula for alkane. So for whatever the number of carbon atom in the molecule, the number of hydrogen atom will be double that number plus 2. To name alkane, we know how to use the prefix. The prefix refers to the number of carbon atoms, and then the suffix is going to be "ane". So these are the first four members of the alkane homologous series: methane, ethane, propane, and butane. The molecular formula CnH2n plus 2. So you can simply find the molecular formula for each of these members. and this is the structure formula for the different compounds and how to draw them using the displayed formula. As you can see, you have to draw all the different elements within the compound with their bonding. Remember that when you draw any compound, carbon atom must have four different bonds, and here for methane it's only with hydrogen, for ethane it's one with another carbon atom and then with hydrogen, and so on. The first physical properties of alkane boiling point: as the number of carbon atom in the chain increases, there is an increase in the boiling point of the compound. And the main reason for that is because of the increase in the intermolecular forces between the compounds. So increase in the intermolecular forces will lead to a need for higher energy to break the bond between the compounds. Reactions of alkanes. Alkanes are fairly inert because they only have a single bonds, which is between carbon and hydrogen or between carbon and carbon. So they do not tend to react easily, and they are very unreactive. So the only possible reaction for alkane is the reaction of alkane with halogens such as chlorine and bromine, which only react in presence of UV light. In this reaction, something if you have an alkane like methane and you reacted with bromine in presence of UV light, there will be a substitution reaction where one hydrogen from the alkane will be substituted with one bromide to give you bromoalkane, or will give you bromomethane in this case, and hydrogen bromide. This reaction will only proceed in presence of UV light. Alkanes, we know that alkanes or hydrocarbon are mainly used as fuel, and this is because they undergo complete combustion in presence of oxygen. So, in presence of excess oxygen, where they will undergo complete combustion, where they will completely be oxidized to give you carbon dioxide and water. The main reason why this can be used as a source of energy or as fuel is because this reaction is an exothermic reaction, and it produces a lot of heat, so it can be used as a source of fuel or as a source of energy. The incomplete combustion: if there isn't enough oxygen, alkanes can undergo combustion, but this is going to be incomplete combustion. Incomplete combustion here, the hydrocarbon will not only give you carbon dioxide and water, but also will give you carbon monoxide and carbon, which is soot. So this is represent one of the problems of using alkanes as a source of fuel or as a source of energy. Carbon monoxide is a problematic because it cannot be seen, cannot be smelled or heard, and it's a silent killer because carbon monoxide tend to bind to the hemoglobin and the red blood cells with much higher affinity than the oxygen, where hemoglobin is responsible for moving the oxygen around your body, and carbon monoxide will bind to the hemoglobin instead of the oxygen, so there will be no oxygen and there will be suffocation. So this is the problem of carbon monoxide. It's called a silent killer. Hydrocarbons and alkanes are used as fuel. However, there are many problems of using hydrocarbons as source of fuel in the car engines. And you probably heard of the acid rain. So how is the acid rain produced? The car engine has very high temperature, and this very high temperature in the car engine leads to reaction between nitrogen and oxygen from air, and that will produce nitrogen oxides such as NO and nitrogen dioxide NO2. Also, the different hydrocarbons can contain, in addition to containing hydrogen and carbon, they also contain some sulfur. And when they are burned, either in cars or any other source, just when they are burned, the sulfur that we can find in the different sources of the hydrocarbon can react with oxygen from air, and that will give you sulfur dioxide. The acid rain comes from these oxides, nitrogen oxide, nitrogen dioxide, and sulfur dioxide. So all of these will be released into the air, and when there is rain, the water from the rain, these oxides will then dissolve in the rain to give you acids such as nitric acid and sulfuric acid. And these acids are the source of the acid rain. The problem with the acid rain is that they cause corrosion of rocks and buildings. They alter the pH of the soil or rivers, which can affect the ecosystem, and they also corrode limestone, which damages buildings and statues. So all the hydrocarbons come from crude oil. So how is crude oil formed? Crude oil comes from the remnant of the living organism that lives millions of years ago. These have been buried under the soil for a very long time, and they have been subjected to high pressure and temperature, which has changed them, and they turned them into crude oil. The crude oil is then extracted from either under the water or from under the soil, and then they are used as a main source to get the different hydrocarbons. The main problem with crude oil is that they are non-renewable, finite resource of a hydrocarbon. So the crude oil contain mixture of many different hydrocarbons, and they have to be separated before the hydrocarbons can actually be used. We cannot use the crude oil as it is. To do this, we use the fractional distillation of crude oil. In the fractional distillation, we use a furnace and we use a fractionating column. The crude oil is fed into the furnace where it's heated to very high temperature, and then the different component within the crude oil will start to boil, and they will go through the fractionating column. In the fractionating column, the oil will evaporate and it will condense at a number of different temperature, because the fractionating column has different temperature, and the temperature will be less as we go up in the fractionating column. So at the very bottom, it's very high temperature. As you go up, the temperature will decrease gradually until we reach just 20 degrees at the top of the fractionating column. So at the top of the fractionating column, the gases will be easily separated there, such as butane and propane. As you go down, the different fraction will be separated based on their boiling points, and usually hydrocarbon which has similar number of carbon atoms will have similar boiling points, so they can be separated as fractions. So there is petrol and then kerosene, diesel, and fuel oil. At the bottom of the fractionating column, lubricating oils, paraffin, soot, and asphalt and wax can be separated. These have very high boiling points and usually separated because they are solids at the bottom of the fractionating column. So in the fractionating column, the gases will be separated at the top, the solids will be separated at the bottom, and as you go down, the boiling and viscosity of the different members will be increased. Crude oil has many uses because it provides the fuel for most of the model transport, and also the diesel oil, kerosene, and heavy fuel oil all come from crude oil. In addition, that the petrochemical industry uses the different hydrocarbon that come from the fractional distillation, and they can be also used as in making different polymers, solvents, detergents, and lubricants. Most of the fractions that are separated using the fractionation of the crude oil are long chain hydrocarbons, which are much less useful than the short chain hydrocarbons. And in order to use these long chain hydrocarbons and make them more useful, we use something called cracking, where the long chain are broken down to give you shorter chain hydrocarbons, which are much more useful than the longer chain hydrocarbons. And cracking, the hydrocarbons is heated until it's completely vaporized, and then they can either be broken down using catalytic cracking, where the vaporized hydrocarbon are passed over a hot catalyst such as silica or alumina, where they are broken down to give you shorter chain hydrocarbons. Or we could use the steam cracking, and in steam cracking, the vapors of the hydrocarbons are mixed with steam and heated to a very high temperature that can reach up to 600 or 700 degrees so that thermal decomposition will then occur. And cracking, the products of cracking will be shorter chain hydrocarbons, alkanes, shorter chain alkanes, and also alkenes. Sometimes in your exam, you will be asked to try to draw or to balance chemical equations for cracking. And normally, the long chain hydrocarbon for the alkane will give you shorter chain alkane and an alkene. For example, if you have something like octane, which has 8 carbon atom, when we do the cracking, we can end up with hexane with 6 hydrogen atoms, 6 carbon atoms, and ethene, which is the alkene, a small alkene, the simplest alkene. Alkene is the second homology series you need to learn about, and alkenes are unsaturated hydrocarbons. They have the general formula CnH2 when they are unsaturated because of the presence of the double bond between two carbon atoms. The simplest alkene here is the ethene or ethylene, which has only two carbon atoms and a double bond between the two carbon atoms. The functional group for the alkene is the carbon-carbon double bond. To name the alkene, we're going to use the exact same general rule we used. So alkene are named by counting the number of carbon atom in the chain, and then we will give the prefix which refers to the number of carbon atom, and then the suffix will be "ene," which refers to alkene. These are the first four members of alkenes that you need to learn about. The first member will have a number of two carbon atoms because you cannot have a double bond from one carbon atom. This is the ethene, which has this double bond. And then we have propene, which has three carbon atoms. This is the double bond. And then we have butene. Butene can be either one butene or two butene. So you could have the double bond between the first carbon atom and the second carbon atom, or you could probably have it between second carbon atom and the third carbon atom. So these two are isomers. As we said, they are position isomers. Both of them have the same molecular formula, but they have the position of the double bond or of the function group is different. So you have one butene and two butene. Alkenes. So one of the main reaction of alkene is the addition reaction. So addition of halogens. The addition reaction is the type of reaction where the double bond of alkene is broken down here and two different atoms are added. So alkenes can react with bromine to give you 1,2-dibromoalkane. And also chlorine can react with alkenes to give you 1,2-dichloroalkanes. So one of the main uses of this reaction is the use of bromine water to test for the presence of a double bond. Bromine water is orangey in color, and if you have a sample that you suspect it might have a compound with a double bond, you can add 1 or 2 drops of bromine water and shake your solution. If the color disappears, that means there is a double bond because bromine has reacted with the double bond was added to give you the 1,2-dibromoalkane. Alcohol is the third series that you need to learn. Alcohol contains the functional group OH. And to name the alcohols, you also gonna follow the same concept for naming the organic molecules. The prefix will refer to the number of carbon atoms, and then we gonna have the suffix "ol." So methanol is the first member, and which has one carbon atom and OH, and then ethanol is the second one with two carbon atoms and an OH, and then propanol, and then butanol. Ethanol is an alcohol that is found in beer, wine, and in alcoholic drink. Ethanol has two carbon atoms. This is the first carbon atom and this is the second carbon atom. It's used as a fuel for vehicle either on its own or mixed with petrol. Ethanol can be produced either by one of two ways. The first way is by using ethene and steam using acid as a catalyst. So when you have ethene and then you add water to it, this in presence of an acid, and the acid can be sulfuric or phosphoric acid, that will give you the ethanol. Ethene is produced from crude oil via cracking, as we have seen. And then the steam here, the addition of water of steam is called, this type of reaction is called addition reaction, as we have seen also with alkenes with halogens. The addition here because the double bond was broken and then the water molecule was added, well, an OH was added to one carbon and a hydrogen was added to the other carbon to give you the alcohol, the ethanol. The acid used, as we said, could be phosphoric acid or sulfuric acid. The reaction needs high temperature that can reach up to 300 degrees, and also we use pressure for 60 to 70 atmosphere. This reaction for production of alkane has advantages and disadvantages. The main advantages is that it's a very cheap reaction and there is no waste is produced. However, the main source of the ethanol is ethene, which is produced from crude oil, and we know that crude oil is a non-renewable source of energy, and so it will eventually disappear, and then the whole process is going to be very expensive. So there's another way of producing ethanol, which is the fermentation of sugar or fermentation of glucose as one of the examples of sugar. There is an advantage for this method over the other one because glucose or sugars is considered as renewable source for the production of ethanol. And here is ethanol is manufactured by the fermentation of glucose in the absence of air at an optimum temperature of 30 degrees using an enzyme in yeast, where yeast is a type of a single-celled fungus which provide the enzyme needed for the fermentation. So this is an enzymatic catalytic reaction. So we know that enzymes will always have optimum conditions for the reaction. So what are the optimum conditions for the fermentation? First, the temperature must be between 25 to 35 degrees. If the temperature is low, then the enzyme will not function, will be inactive. And if the temperature is too high, we remember that enzymes are proteins, and at high temperatures, protein will be denatured, so they will be completely inactive or will be destroyed. They usually need to be done under slightly acidic condition, and they need to be in the absence of oxygen. So air must be kept out. The main reason for that is because ethanol in presence of oxygen will be oxidized to give you ethanoic acid. So you will not end up with ethanol, but rather with the acid. One of the main problems of this method is that the ethanol that is produced is very diluted, and we need to concentrate it and we need to purify the ethanol before it can be used. So concentration of ethanol from the fermentation mixture is quite important. First of all, when the ethanol concentration reaches 15%, the yeast will die. So you have the mixture now will contain the yeast and yeast cells and some insoluble substances. You need to separate these by filtration, where the yeast and insoluble substance will be separated, and then you have the filtrate will contain ethanol and water. Then you need to separate the ethanol or concentrate the ethanol by using fractional distillation, which will give you concentrated ethanol. In the fractional distillation, we can use fractional distillation because the boiling point of ethanol is less than the boiling point of water. The main reactions of alcohols, we said that alcohols can be oxidized, so alcohols will be oxidized to give you carboxylic acid. The example of oxidizing agent that can be used is potassium dichromate 6 in dilute sulfuric acid. So you can use any alcohol in presence of potassium dichromate and dilute sulfuric acid, and that will give you the corresponding carboxylic acid, which is the carboxylic acid with the same number of carbon atoms. So ethanol will give you ethanoic acid. Also, microbial oxidation of alcohol is possible, so some microbes will use ethanol as a source of energy, and as they do so, they will oxidize the ethanol using air, the oxygen from air, as oxidizing agent. The carboxylic acid will be produced as a side product of this reaction or of this oxidation. Alcohols can also undergo complete combustion in the same way as hydrocarbon. This is why they are used as fuel. So they can be completely oxidized in presence of oxygen and could undergo complete combustion to give you carbon dioxide and water. An example is ethanol in presence of oxygen will give you 2 carbon dioxide plus 3 water molecules. Carboxylic acid is the fourth homology series you need to learn about, and carboxylic acid have the carboxyl group functional group, and the carboxyl functional group consists of a carbon with a double bond with an oxygen and also connected to an OH group. So this is as a whole is called a carboxyl group. Carboxylic acids are named in the same way, where the prefix refers to the number of carbon atom and the carboxylic acid, including the carbon that has the carboxyl group. And then we have the suffix oic acid. So the first member is methanoic acid, which is the simplest carboxylic acid. The second member with 2 carbon atom is the ethanoic acid. Ethanoic acid is the acid that we find in vinegar. These are the first 4 members of the homology series, which are methanoic, ethanoic, propanoic, and butanoic acid. And there is an increase in the number of carbon atom from 1 to 3 and 4. And this is the functional group of the carboxylic acids. Carboxylic acids are typical acids, so they are weak acids and they have the typical acidic properties. So they dissolve in water to produce an acidic solution of a pH less than 7. They react with metal carbonate to give you a salt and carbon dioxide. Carbon dioxide can be recognized as bubbles or effervescence. For example, ethanoic acid in presence of sodium carbonate will give you a sodium ethanoate, carbon dioxide as a gas, and water. They also react with more reactive metals to produce salt and hydrogens, and hydrogen here can be also recognized, or we can see the reaction or know that the reaction has happened because there will be bubbles of hydrogen. So ethanoic acid with sodium will give you sodium ethanoate and hydrogen gas. And finally, because they are acid, they will react with bases to give you salt and water. So the main source of the acidic properties is the carboxylic acid group. The hydrogen, this hydrogen is acidic. So how carboxylic acids are formed? We learned about the oxidation of alcohols. So they come from alcohols. Oxidation of alcohols will give you the corresponding carboxylic acid with the same number of carbon atoms. So ethanoic acid will give you oxidation of ethanol will give you ethanoic acid, and oxidation of one propanol will give you propanoic acid. Oxidation of one butanol will give you butanoic acid. The final homology series is the esters, and esters will have the function group COO. Esters are formed by a type of reaction called condensation reaction between alcohol and carboxylic acid. And condensation reaction are reactions where a water molecule is removed, and as the water molecule is removed, the OH will be removed from the carboxylic acid, and the hydrogen will be removed from the alcohol. So If you have something like ethanol and ethanoic acid and they react together in a condensation reaction, OH will be removed from the ethanoic acid and the hydrogen and they will combine together to give you the water molecule, and then the oxygen from the ethanol will then be bonded to the carbon from the carboxylic acid and they will give you the ester with this functional group, the ester functional group. To name the esters, we need to start off with the name of the alcohol part first. So the alcohol part here was ethanol. So this is going to be called ethyl as a prefix. And then we're going to name the carboxylic acid part then. So here we have ethanoic acid with two carbon atoms. So this is going to be called ethyl